So over the past two videos, we looked at two examples of using this concept of a U substitution to evaluate some more complicated definite integrals. In example 3 here, I have three more examples that I'm actually going to ask you to spend some time trying to work through. Now, I'm going to kind of layer this video up in a couple different ways. I'd like us to try to go ahead and pause here at the start so that you can attempt each of these problems. And you may get through them successfully, you may not. It just kind of depends. Now, if you're getting stuck, you can go ahead and unpause the video and you'll be able to see me at least give some general hints as maybe what to use for the value of U. In fact, I'll probably generally for most of these just outright tell you a good value that you could use for your substitution. I will not, though, however, show the full solution to each of these questions, and I'll save that to I'll save that for you to go look at in the full solutions that are posted up online in Blackboard. But this will still be a really good opportunity for you to kind of practice right now with how well do you really understand what we've talked about thus far. So go ahead, pause the video here, try to work through parts A through C, at least a little bit on each of them, if not all the way, and then you can unpause the video to go ahead and see some additional hints as to what you could use for good substitutions. All right, well, hopefully you actually did go ahead and try some of these out. Here's at least what I would tend to use for you on each of these individual questions. For the first one here, I think a great selection for the value of U would be this 3 minus 5x. Notice that would allow me to kind of turn my integral into something like over a U squared, which I could rewrite at some point as U to the negative second power. So you can go ahead and try that one out if you hadn't already attempted that. And if you did, you can take a look at the full solution online to see if you got the right answer. Now in part B, I would go ahead and I would actually let U here be equal to the natural log of x. Notice that the derivative of this will be 1 over x, which you already have inside of the integral. Finally, for part C, I would go ahead here and actually perform a little bit of an algebraic simplification because it's hard to see a substitution that would work here. This is actually a fairly challenging one. What I would do here is I would rewrite this as e to the x times e to the x. Remember that when you have a power of things that are being added, like if I add x to the 2 plus 3, that's x to the 5th power, that is x to the 2 times x to the 3, right? When I have things with the same base and they're multiplied together, I add the powers. But now, notice that once I'm here, I actually have a really easy substitution that I could make. Pause the video again really quickly if you want a chance to try to think about it yourself. All right, so what I would have selected here for my value of U, once I've made this algebraic move, would be e to the power of x. Notice what I could do is I could replace this e to the x with the value of U, and this stuff here at the back could actually become equal to du. And so this integral here will actually simplify up really, really nice. You may not actually end up with a very simple final answer. It may look a little bit ugly, but the integration process will be very, very straightforward. Make sure, though, that with each of these parts, A, B, and C, you did go through and actually confirm that your function was continuous on the given interval. Remember, if your function is not continuous on the given interval, the only thing you would ever have to write is that the function isn't continuous on the interval and that we cannot proceed in Calc 1.